So let me try to take another stab at this, and then we'll go back to that calculation that I, messed up, ending the lecture on a high note. So I'll try to do better, but I really want to, I think this two-dimensional business is really not that big of a deal. It's just that I don't think I explained it very well. So let me try it again, and hopefully that'll, hopefully you'll see it a little bit better. So let's do something very simple. So I'm gonna stick with flat space-time. And I'm going to stick with Cartesian coordinates. So first, let's reflect back on what we did in the time-like case last week. So suppose I take a congruence of null time-like geodesics, and I'll take the simplest thing I can think of. I'll take a congruence of time-like geodesics where x, y, and z is constant on each one, so that each curve is moving straight in the time direction. So that's really, a very simple congruence. And the point I want to make here in the time-like case is that if we consider the hypersurfaces orthogonal to that congruence, because clearly it's a hypersurface orthogonal congruence, the hypersurfaces that are orthogonal to those are the surfaces of constant t, right? So all the lines are moving up here, and then we take a cross, we take a surface across that, and those surfaces are t equal constant surfaces. And if I want to look at the metric on those hypersurfaces, well, what I need to do in the space-time element is to just get rid of dt squared, because dt is 0 on each one of those hypersurfaces. And that's just a statement that on those hypersurfaces, obviously I kill one dimension, and my effective metric, my induced metric on that hypersurface is going to be a three-dimensional metric. So here at this level, I don't think there's any mystery. That's why, because the metric on each hypersurface turns out to be three-dimensional, that's why we're talking about cross-sectional volumes, because each one of those hypersurfaces is what I would mean by the cross-section of the congruence, and the cross-section is three-dimensional, and therefore we're talking about three-dimensional volumes. And again, in the time-like three-dimensional case, if I want to go from the space-time metric to the three-dimensional induced metric on each hypersurface, the tool to do that is the h alpha beta that we defined in the time-like case, where we take the original metric g and add the UU term. The UU term has the purpose of killing off that t dimension over here, and what's left over when you look at h is a purely three-dimensional metric that is really a metric on those hypersurfaces that are orthogonal to the congruence. So in the time-like case, I think there's no big mystery, and the h alpha beta, continues to be meaningful even when you don't have a congruence that's hypersurface orthogonal. So now let's do the same thing in the light case again, just to try to understand a little bit better what was going on this morning. So suppose that I pick again the simplest congruence I can think of. I'll pick my tangent vector field k to be such that I'm moving along the t and x direction, and that's it. So I'm moving with the speed of light in the x direction, so I have a bunch of null rays all moving in the same direction and only moving in the x direction. So that's the that's the tangent vector field, and if I look at the vector k with the index down, I find that it's 1, 0, 0. And what I find because of that is that it's actually the gradient of some function phi, and the function phi is equal to t minus x. And those are the surfaces to which the congruence is orthogonal in this weird sense where, the null rays are all going like this in the positive x direction. For you, that's the positive x direction. But the surfaces are also in that direction, so the geodesics are actually tangent in addition to being orthogonal to that hypersurface. That I cannot explain any better. It's at once normal and tangent to the surfaces. Okay, But now I want to play the same game, and what I want to do is to consider induced metric on those surfaces that I'm defining here, the surfaces of constant phi. And a good way of doing this to construct that induced metric is to switch coordinates. Instead of t, I'm going to use phi as a coordinate to describe my flat space time. And the interest of doing that is that I can identify the induced metric on phi equal constant hypersurfaces by putting in d phi equals 0 in the metric. Right? So we're going to be using phi as a new coordinate, which means that dt in the metric is going to be expressed as d phi plus dx. And when I make the substitution, I find that, well, we get minus d phi squared. Then we get minus 2 d phi dx. Then I get minus dx squared from up here, but I kill that because of the plus dx squared that was there originally. And then we get dy squared and dz squared. So that's the metric, the full metric of flat space-time expressed in a new coordinate system that's adapted to my adopted null direction. Right? So if I want to know what is the induced metric on the surfaces phi equal constant, well, all I have to do is to say that on those surfaces phi is constant, right? So I kill off this term, I kill off this term in the metric, and what I find is what I found before this morning, that what's left over is not a three-dimensional metric, it's a two-dimensional metric. And that has to do with the fact that, we get this degeneracy in the metric that comes from the null direction, and that's something that's, a very, generic feature of working with null surfaces, that the induced metric on those null surfaces is degenerate, and in fact, it's, in this case, directly, two-dimensional. So that's what I was trying to say this morning, and I think it comes straight out of this very simple calculation, and that shows that when we're talking about null surfaces, null congruences, what we don't expect, so what we expect, the H alpha beta quantity, we expect that to describe a two-dimensional metric, not a three-dimensional metric as we had in the time-like case. And in a similar way, we don't expect to have cross-sectional volumes anymore. What we'll have are cross-sectional areas, and basically everything becomes effectively. So I hope this helps. At least it's a more direct, way of saying what I was trying to say this morning. So that's more of this, the same along the theme that, playing with null curves, null geodesics, or null surfaces tends to be weird, and you tend to lose one dimension like this, and you have to be very careful and think about this very carefully. Now, just to complete this story, if we want to go from the full spacetime metric down to the metric on each hypersurface phi equal constant, well, what we need to have is an H alpha beta that will have this property of being two-dimensional. And that's the thing that I constructed this morning, the G plus, NK plus KN. That thing is what is doing the right thing. So if I complete the calculation here and I consider an n vector that would be equal to 1/2 1 minus 1, 0, 0, that's the vector that points in another null direction, complementary to this first null direction over here. Well, the construction that I had this morning, where you just take the original metric and you add the Kn plus Nk things to it, that is something that turns a four-dimensional metric into an induced metric on those surfaces that's explicitly two-dimensional. So basically, that's why it's a bit more complicated, because we have to kill off two null directions to go from 4 dimensions to 2 dimensions, whereas before, in the time-like case, we only had to kill that one time-like direction. So basically, that's what I was trying to say this morning. I hope it's a little bit clearer now. Is it clear enough anyway? So, yep.
This is the only way phi equals t minus x. This is the only only way to construct these hypersurfaces that would give us the k vectors?
Yeah, well, so the way it works is that first you're given the k vector. So first you're given the congruence.
Yes.
So you're given the the tangent vector field everywhere. And then you can check whether or not, and that may not be true. So, here I'm considering a case where k will be proportional or even equal to a gradient. That I get, by calculation. So phi, well, apart from constants, that's the only function such that the gradient is equal to k. That's a relationship that may not hold in general, so I may not have a hypersurface orthogonal congruence. What was your question?
So is it a unit, this phi, or is it?
It's a family.
It's a family, right, apart from constants.
Yeah, apart from, so yeah, so.
I'm not worrying about.
So phi is constant on each hypersurface. But yeah, it's unique because, well, you just integrate this, right? So you just construct a phi such that the gradient is everywhere equal to that, and it's a unique solution apart from constants.
Sorry, the question was stupid, I'm sorry.
No, I don't think it was. It's a good question. Any other questions? Okay, so let me now go back to the calculation I was trying to do previously. So just to recap, so we have this transverse metric that now we know how to construct. And it has all those properties that I listed before. We have the deviation vector that satisfies this equation over here. Sorry, that's C. Where B alpha beta is again defined to be the gradient of the tangent vector field. And that is something that tells us something about how Xi varies as we move up along the congruence. But as we talked about this morning, we have to do a little bit more work behind this because we want to kill off an eventual component of Xi along the direction of K. And as we saw this morning, we need to apply the projection operator to do that. So that's not quite the starting point we want, but it's going to be part of the calculations we have to do. One thing I didn't say this morning I should have is the statement that, like what we had before, B is orthogonal to K. For the same reason that B was orthogonal to U in the time-like case, it's exactly the same calculation. So from this angle, we get that K alpha beta is just K alpha semicolon beta, but that's just the same thing as half K alpha fully differentiated with respect to beta. And because, K dot K is 0, this is 0 everywhere. And then from the other direction, this is K alpha beta, semicolon beta K beta, and that's 0 because of the geodesic equation. So our tensor B is orthogonal to K, which is a good thing, but we're going to want to turn it into something fully transverse by making sure that it's also orthogonal to N, right? So what we're trying to do here is to make sure that everything is defined only in the transverse space so that we can really talk about the transverse properties of the congruence. So having selected a reference geodesic, I want to talk about the deviation vector in the transverse subspace. I want to talk about the relative velocity in the transverse subspace, and I want to do everything in the transverse subspace. So we have these properties, but these guys are not 0. There would be no reason for that to be true. Okay, so that just means that we need to put a little bit more refinement to this to achieve what we want to achieve, which is, again, a purely transverse description of what's going on. Okay, so going back again to what we were doing, we've defined this to be the transverse part of the deviation vector. And that has, the required properties of having no components along K, no components along N, and only components in the transverse subspace. So that's where we were. And what I was doing before we broke for lunch, I was in the middle of calculating the rate of change of that vector as we go up the congruence. So let me just start from this definition. So we take all of this and we differentiate with respect to K. So first I get the transverse metric differentiated. And we're going to have to calculate that. And then we get the transverse metric multiplying the, the gradient of C in the direction of K, which is just given by our B tensor over there. So this is B mu beta C beta. So I'm going to leave it at that. I want to work on the first term. This over here is the metric plus the other two terms. And all of that I differentiate with respect to beta, and I take that in the direction of K. Is there? Where is what, sorry? Oh, there's a C missing, that's right. Thank you. Right. Okay, so the first term gives me nothing. The second term, if I differentiate K alpha and then I do that in the direction of K, I get 0. But I won't get anything, I won't get 0 from here. So this is equal to K alpha that multiplies N mu differentiated in the direction of K. And this I multiply by C. And then from the second term, I would get, so I differentiate N in the direction of K rho, but then I multiply by K and C together, and that's 0, right? So K and C was, was declared to be 0. So K was declared to be equal to C at the very start. So that term is 0, and now what I have to do is to keep N alone. And, well, again, I get 0 because when I differentiate K in the direction of K, I also get 0. So from that little calculation, I only pick up one term. So what do I get? So going back to the full calculation, we get this guy over here, the last term. I'll write it first. And then I get an additional term, which is C mu and mu differentiated in the direction of K, and all that multiplying K. Okay. What I'm trying to do here, again, is to define something like a transverse velocity between two neighboring geodesics. So a velocity that would be defined in the transverse space. What I was trying to do is, well, first what I did was to define a purely transverse deviation vector, and then I differentiated that along K, and that's a notion of of relative velocity between my neighboring geodesics. But I recognize here that I have a term along k, which means that this vector that I'm constructing here, this relative velocity, is not quite the one I want because it has a component to b. And what I need to do is to kill that by, again, taking a projection into the transverse subspace. So this is what I get. I can't deny this. But what I can say is that this is not quite the notion of relative velocity I wanted to have. The one that I really, so the notion of relative velocity I really want to have is the one where I take this and I project it down to the transverse subspace. So the transverse relative velocity between neighboring geodesics is this vector that I just calculated that I'm going to project. In other words, I'm going to take this, so there's an alpha over here, and I'm going to apply a projection operator on that. And this is going to be the notion that I really want for, for a relative velocity vector that has this property of being purely transverse. Which means that I'm going to get, from this line up here, I'm going to get h alpha mu. Over here, I'm rewriting the indices here, so it's going to be h mu. So instead of calling this, so this was xi alpha differentiated, now I have xi mu differentiated. So this alpha has been turned into a mu. I'm going to turn this mu into a nu to make sure that I don't confuse indices. And after projection, I don't get that. Right? So now I'm happy because everything is properly, projected down to the transverse space. And I can even simplify this a bit because here you notice that I have two applications of the projection operator, and that's as good as having one application of the transverse operator. One thing I can do also is to replace this by xi beta with a tilde on it, plus whatever term I need to make this right. So, there was a xi dot n component here along k. So the difference between the original xi and the projected xi is something that involves a term in k. So that's something, I didn't write it down on the left, but that's something we saw this morning. Something that comes out of that projection operator over there. And the point is that it makes no difference because b is orthogonal to k, right? So it doesn't matter here whether I'm dealing with xi or xi tilde. It's the same thing after multiplication by b. So what do I get after all this? I get h alpha nu b nu beta, and then I get xi beta. Yep.
Before taking the transverse xi, we had taken the covariant derivative of xi.
Yep.
And then taken the transverse.
Only after taking the velocity. You would have ended up with a lot more terms in k or n. And but after full projection, it would have all settled down anyway. So I think you can proceed like this.
So it would settle to the same thing?
Yeah, I think so. I'm not completely sure, but I think so. So what I prefer to do is to just take a projection at each step, and then that's what we get. But I think if you projected just at the end of it, I think that would be it would be the same thing. Okay, I'm going to do one more thing, and it's going to seem silly. I'm going to express this as h beta, I don't know, gamma, xi gamma. I really don't need to do that, but I'm going to do it anyway. This is already obtained from xi by an application of the projection operator. What I'm doing here is to apply with the projection operator again. And it makes no difference because one application is just as good as two applications. So this makes no difference. But the reason for doing this is that now I have the two projection operators acting on B and I can define a purely, a purely projected B out of this. So just to finish off here, we get H alpha nu, H beta gamma, multiplying B and multiplying C gamma. And the reason why I wanted to do this, as I just said, is because I want to apply the projection operator on each index on B and define that to be a fully projected B. And let's see, this would be B alpha gamma. Okay, so that's my final result. So the purely transverse velocity between two neighboring geodesics so the fully projected thing is then a fully projected B multiplying a fully projected C. And that's a neat way of expressing all of this. And then B alpha beta is just the same thing as H alpha mu, H beta nu acting on the original B. So at this stage in fully projected form, I have what I really want. I have something involving a projected deviation vector that lives purely in the transverse space. I have a purely transverse relative velocity between neighboring geodesics, and all of that is expressed in terms of a fully transverse B quantity, which is the analog to what we had in the timelike case, where projection was all irrelevant because it was all built in. Now we've got everything down in the transverse subspace, including that gradient tensor B, which is now a projected version of the original one. Just to recall, B mu nu is the original gradient of the tangent vector field. Okay, so this is really the transverse. Well, I wrote it up before. The transverse relative velocity in the null case, all fully expressed, as I just said, in terms of fully projected quantities. And it's that B tensor, the projected B tensor, that I want to now decompose into irreducible quantities. So in the same way we did before, but now we do it purely in the two-dimensional subspace, we're going to be decomposing B tilde alpha into a trace part, a symmetric trace-free part, and then an antisymmetric part. So that's the decomposition into irreducible parts. Theta is going to be the expansion scalar in the null case. That's given by the trace of the projected B. But because B tilde is now fully orthogonal to both K and N, taking the trace with H or taking the trace with G is exactly the same thing. And if you boil it all down, I'll do the rest of the calculation in a second, but after some steps here, you find that this is just, again, the usual four-dimensional divergence of the vector field K. I have to complete the calculation to convince you that this is really true. The shear tensor, so this is the expansion. The shear is going to be the symmetric part of B tilde minus the trace. This is the shear tensor. And the rotation tensor would be the antisymmetric part. of B tilde. And that's the usual decomposition. The only thing that changes is that because in two-dimensional transverse space, instead of a three-dimensional transverse space, basically we're losing some components. And instead of having a 1/3 here, we get a 1/2. Because when we take the trace over h, we get a 2 instead of a 3. The interpretation of these things is more or less along the lines that we saw before, except that, again, we're dealing with a two-dimensional space instead of a three-dimensional space. And one thing that changed, though, is that instead of having the rate of change of cross-sectional volumes, the expansion now is going to refer to cross-sectional areas. So because my induced metric in the subspace is two-dimensional, when I take a cross-section of the congruence, I get areas, I don't get volumes. And what will change under the flow of the congruence is going to be those areas. And theta is going to be the rate of change of the fractional rate of change of cross-sectional areas. So after you do all the projection business, pretty much everything is back to where we were in the three-dimensional case, well, in the timelike case, except for this loss of dimension. But other than that, it's pretty much all the same. Okay, let me fill the gap here, and let me be a bit more explicit about B tilde, because here I have it in definition form. It's good to expand this out so that we know a little bit better what it stands for. Okay, so let's calculate B tilde. So B tilde, we just applied the definition. So the first H is delta mu alpha plus k mu n alpha plus n mu k alpha. So that's the first H. The second H is delta nu beta plus k nu n beta plus n nu k beta. And all of that is acting on B. So let's just multiply through. So I'll consider these factors first. So first we act with the Kronecker delta. So we change the nu into a beta. So we get B mu beta. And then we get 0 because k multiplying B gives 0. But this guy is n multiplying B, and that's not 0. So the second term that we get is plus k beta, and then we get n multiplying B, and that's not 0. So we have to keep that. Okay, so it's not so bad after one stage. So now let's multiply this through. So apply the delta on that. So we change the mu into an alpha. So we do that here, and we do that for the second term. So that's this multiplying all that. Now we multiply this by all that. And here again we get 0 because k will multiply b, and that's 0. And k will multiply b again here, and that's again 0. So nothing comes from the middle term, but now we're going to get a whole bunch of terms from here. So now we get k alpha, and we get n multiplying b. And here we get k alpha, k beta, and we get n mu n nu multiplying b. And that's our final result. The projected b is the original b plus a term in k alpha that multiplies n mu multiplying b. Then we have a term in k beta that multiplies n nu multiplying b. And finally, we have k alpha, k beta that multiplies n multiplying b. So that's a handy expression. So basically, we know that this has no components along k or n. That's true by construction. This had components along k that are killed off by this, and that, k and n. So those terms here are designed to kill off the ones that were originally here, so that this guy here has no components along k and n. It's a purely transverse tensor. Okay, why did I need this? Well, now I want to go back and take the trace and see what we get when we take the trace. When we multiply on the left by the metric, the inverse metric, so from here, we get the trace of the original b. When we raise the index here, we end up multiplying k by b, and that's 0. When we apply the inverse metric on this, we end up multiplying k by b, and that's again 0. And here we end up multiplying k with itself, and that's 0. So in fully projected form like this, it's obvious that we get nothing else. And this, of course, is the gradient of k. And as advertised before, we get the four-dimensional divergence of the k field. All right. So one thing that's coming out of this, to go back to something we talked about this morning, so we all recognize that the choice of n is not unique. N has 4 components, but we only give it 2 constraints. So that there'll be lots of solutions to that. It's not a unique solution. As a result, the transverse metric is not unique, and the selection of the transverse space is not unique. So that's something we have to live with. B tilde, because it depends directly on h, is also not going to be unique. So the choice of n will influence the choice of h, and then everything else that follows from that. But theta, the trace part of B tilde, after doing this calculation, we notice that it's independent of n, independent of that choice. So one very important property of the congruence, the rate of expansion, is something that's independent of that null direction. And that's useful information. And then there'll be other things that, that also will be invariant under a change in n. In one of the next homework problems I'll give you, I'll ask you to work this out completely. So what happens if you pick a different n that also satisfies those definitions, but it's a different n, and what are the changes that would occur in all the quantities that we're constructing here, that we're calculating here. So one thing you would find out is that by doing this calculation is that, okay, even though theta is invariant under a change in n, the shear tensor will depend on the choice. And the rotation tensor also will depend on the choice. So those things are not unique. They will be impacted by the selection of the vector n, but nevertheless, there's still some invariance properties that these guys will satisfy that I'll talk about in a moment. All right, any questions about that? Yep. Yeah, I'll just keep it here. Yeah, I can't move the other one. Okay, any other questions? Okay, yep.
When you say the rotation depends on your choice, I assume that if it's 0, it'll be 0 for all choices.
Yeah, okay. I was going to say that in a moment, but that's absolutely true. Because, of course, one of my next topics is going to be the statement of Frobenius theorem, and we're going to be establishing that when omega is 0, we have hypersurface orthogonality, and that has to be invariant under a change in n, and that's going to be true. Okay. In fact, I was ready to talk about that right now. So that's just the basic setup. So we have our basic kinematic quantities here, the tangent vector field. We have, the projection operator that allows us to define the transverse subspace. We have the, the projected deviation vector. We have the projected relative velocity. We have the projected, B field, which is the projected gradient field for our velocity vector. And then we have our decomposition of the, B tilde into irreducible parts. And each of these things here are characterizations of what's happening to the congruence. It tells us how it's propagating and what the congruence is doing as a result of its flow. And for example, if theta turns out to be positive, we know that the congruence is going to be diverging. If theta is negative, it's going to be converging. The fractional rate of change of the cross-sectional areas is measured by theta. In a little while, I'm going to write down Ray-Choudhury's equation for those quantities, the analog in the null case of what we had in the time-like case. But before I do that, I want to talk about the hypersurface orthogonality condition, and I want to relate this to the fact that in order to have a hypersurface orthogonal congruence, we need to have a zero rotation tensor. I want to keep this one, so I'll move it up. Okay, let's talk about Frobenius. It's pretty much the same story, but because it's null, we have to be maybe a little bit more careful. And we have to be a bit more careful because of the need to project. So I want to run through the argument. So the congruence is hypersurface orthogonal in this weird sense. So maybe I should put it in quotation marks. Is hypersurface orthogonal if my tangent vector field is proportional to a gradient. So that was the condition in the time-like case, and that's also the condition in the null case. And then the statement is that the congruence is going to be orthogonal to surfaces of constant phi. The reason why I'm putting orthogonal in quotation marks is because now we know that what I mean by orthogonal is this weird thing where it is at once normal adjacent to that surface, right? So a null congruence that's hypersurface orthogonal really means that my geodesics are running into the surface instead of running out of the surface we would have in the time-like case. So it's orthogonal in that weird sense that things are orthogonal to themselves. I should really say tangent or surface forming. Congruence is hypersurface orthogonal, or better said, surface forming or surface tracing instead of hypersurface orthogonal. But we're allowed to say orthogonal because, again, K is orthogonal to itself. So K is orthogonal to the normal vector, which is tangent to the surface. Anyway, there's no avoiding that. Okay, so what I want to do is to basically use this relationship here, which is given to us by this hypersurface orthogonality situation, and try to prove that means that omega has to be vanishing. So I'll prove it this way. I won't prove it on the way back. That's a little bit harder, but I think that's going to be enough to sort of tell us that this is really what's going on. Okay. Well, we have the tangent vector field, so I'm going to basically play along with the same method that we used for the time-like case. But what I'm going to have to do on top of that is to take the projection. So I'm going to have to project everything down to make sure that I end up with a statement about B tilde. So the gradient vector is going to be, there's going to be two components to that. We're going to differentiate the scalar function twice, and then we're going to differentiate phi, and then differentiate mu, like that. And what I'm going to do is to then say that B, which is the thing on the left-hand side, is going to be minus mu, the scalar function differentiated twice, and then I'm going to put a 1 over mu here and call this k and call this grad mu. Was there a question? Yeah? Okay. So, same thing. Okay, but B is not what I need, right? So I have B, but what I really need is B tilde. So I need to work out what B tilde is. And B tilde is this big mess over there. So in order to calculate B tilde, I have to calculate the products of B with N. So let me do that. Yeah? Oh, okay. So in all the simple examples that we played with, it turned out that K was not just proportional to a gradient, it was equal to a gradient. That's a little bit too specific. So what I want to say by hypersurface orthogonality is that the normal vector to a surface has to be directed along K. But there's no requirement that they have to be equal to each other. They have to be proportional to each other, not equal to each other.
Because usually in time like this, mu is a factor to normalize the tangent k. But here it's like. So is there a condition on mu?
No, there's no condition on mu. So the point is that, well, K is something that's given to us, right? So we have the tangent vector field. There's no guarantee that K would have been normalized ahead of time so that it would be equal to a gradient. In general, it's going to be proportional to a gradient, so I'm just buying in this flexibility here. So it would be just a little bit too restrictive to make it always equal to a gradient. In fact, at times it's not always true like that. Okay, so that's the reason for including a prefactor to in my relation here. Okay, so going back, so now I have B, I'm in good shape, but I really want B tilde, and in order to get B tilde, I have to calculate all of those things over here. So that's where we need to do a little bit of a side computation. So if I multiply B on the right with N, I'm going to get minus mu, and then the scalar field differentiated twice, and then we multiply by N. And what I get for the second term is K alpha, and that multiplies the gradient of mu in the direction of N. So I have that. If I multiply on the left by N, I get something a bit different. So if I do, so the second term I need is where I multiply on the left, so I get B nu beta in this combination. So now I get minus mu B nu beta N nu for the first term. But here I get minus mu, so here I'm going to multiply N with this K, and I'm going to get minus 1 from that, and I get that as a result. All right. And if I multiply both on the right and on the left, then it doesn't matter how I do it. So if I do it with this guy and multiply by n alpha, I'm going to get minus n mu nu, n mu, n nu. And here I'm going to get, I'm multiplying on the left, so I'm going to get minus 1 mu. There are too many mu's here. D mu mu in the direction of n. Okay, so all of that is a bit tedious, but now we can put it all together. And I'm going to plug all of this into the first expression over here. So I'm going to go to, I won't be able to see the board anyway. So let me go back over here. Okay, so I won't be able to do that in real time, but B tilde is the original B that I had, which is still over there somewhere. So it's minus mu phi differentiated twice, plus 1 over mu. Am I missing minus signs? I'm missing minus signs. No, I have one minus sign. Minus mu, and then plus mu k alpha d beta mu. So that's B by itself. And then I take this guy over here and I multiply by k. So what I get over there is mu nu beta and nu. And then for the second term, I get minus 1 over mu k alpha. And then I differentiate mu, and that's it, in the direction of beta. All right. And then for the other guy, I get everything. So I get a k beta. And then I multiply this guy over here. So I get a minus mu k beta. I get phi differentiated with respect to alpha first. Sorry, I should have planned this better. Alpha first and then mu. And then the other term is plus 1 over mu. I have a k alpha, k beta. And I have mu differentiated in the direction of n. All right, that's what we have. And finally, we have the k beta, the k alpha, k beta term. So now we go back to the last line. We get a minus mu. We get k alpha, k beta. We get phi differentiated with respect to mu and nu, and then we multiply by n. And then the last term, minus mu, k alpha, k beta. And then we get what? We get, again, mu differentiated along n. Okay, well, it's a bit tedious, and it's a bit tedious because we had to do all those projections. But now the good news starts, because we get a whole bunch of things that cancel out. This cancels out with that. And this k alpha, k beta term cancels out with the other one over here. So if I just clean this up a bit, we get that b tilde is equal to minus mu phi differentiated twice. Then we get minus mu k alpha. And we get phi differentiated with respect to mu, and we multiply by n mu. Then we get minus mu k beta. We get phi differentiated with respect to alpha and mu in the direction of mu. And finally, we get k alpha k beta big long expression. What does it tell us? This is symmetric under the exchange of indices, right? If I differentiate a scalar field twice, it doesn't matter in which order I do it. So this is symmetric. This is symmetric. So at least two terms in my b tilde tensor turn out to be symmetric. If I exchange alpha and beta, I get this. So under the exchange, this goes into that, that goes into this. So those two terms together are also symmetric. The only catch here is that, well, I have to switch the ordering here, right? To produce this symmetry, make it obvious, I have to switch the derivatives here. But that's fine because we already know that this operation is a commuting operation. So the point is that the result of this computation is the statement that this is a symmetric tensor. And if it's a symmetric tensor, it means that its antisymmetric part has to vanish. And the final outcome of this is that the rotation tensor vanishes. So the logic, so the proof involves a long computation, but the logic is that we start from this this expression over here, which is just the statement that the congruence is everywhere orthogonal to a family of surfaces, the surfaces of constant phi. So if we have that condition, then we have that k is everywhere along, aligned with the normal vector to the hypersurfaces, which means that it has to have this form. We use this, we accept this, we go through the calculation, and we find that, yes, the rotation tensor has to be equal to 0. So the theorem says that we have hypersurface orthogonality when the rotation tensor is 0, which of course is what we also had in the timelike case. In the timelike case, it was a little bit more obvious, but here we get that, even though the computations are a bit longer. And then, so I proved it this way. With a lot more work, I could prove it the other way around. So the full statement of the theorem is that it's if and only if. So we have a hypersurface orthogonal congruence if and only if the rotation tensor vanishes. And again, hypersurface orthogonality means that we have, a null vector field, and the surfaces to which it's orthogonal is tangent to the so the vector k, the vector field k is at once normal and tangent to those surfaces. So k is both normal and tangent to the hypersurfaces. So we have a whole bunch of surfaces, and on those surfaces we have a whole bunch of null geodesics, and we have a whole stack of those hypersurfaces because we have a whole family of them, and the congruence is is such that they always run tangent to those family of hypersurfaces. Yep.
This theorem only works with null vectors, right?
Well, we had the same statement in the timelike case. right? So we also had that same connection between the rotation tensor and hypersurface orthogonality in the timelike case. Now we have it also in the null case. Yeah. And this version of the proof is restricted to, this version of the Frobenius theorem is restricted to geodesics. In the book, I tell you a little bit more about that, and in fact, there's a version of this that's not restricted to null geodesics. You can have null curves that are not geodesics, and you still have a statement of hypersurface orthogonality like this, and there's an analogous statement that's more general than the one I just wrote down here. Yep.
So you just proved that in the forward direction. If the converse wasn't true, that omega alpha beta equals 0 implies that, then would it still have been a useful statement?
It would what? Sorry.
Would it still be a useful statement if?
Yeah. So if one part was missing, so if we could prove it this way, and not the other way, then it's still useful because if we have hypersurface orthogonality, we can set that equal to 0. So that's still useful. It's more useful if you have it both ways because you can say that, if you have that, then you know that there's a bunch of surfaces to which to which the tangent vector field is. Sorry. If you know that, then you also know that you have this whole family of hypersurfaces to which the congruence is normal or tangent. So so in actual fact, you can prove it both ways, and you have both if and only if. So it works. It works like that. The reason why it's useful the other way is because given k, if you're presented with a tangent vector field k, and it looks horribly complicated, you may not be able to figure out that it's actually the gradient of something. It may be impossible to find, the tangent vector, the scalar field phi, such that that vector field is tangent to it, is the gradient of that. So when you're presented with k, it would be very difficult to integrate the equations to figure out if it's really the gradient of a scalar field. But something that's easier to do, even though there's some steps involved with that, there's an algorithm where you're given k, you pick an n, and you calculate an omega. And if you find that it's 0, then you know that you have a hypersurface orthogonality. And if you know that, you might be more motivated to find a solution to those differential equations that will tell you what phi is. If you didn't know that a solution existed, maybe the motivation would go down a bit. So it's easier to know that you're looking for something that exists than looking for something that may or may not exist. So the needle in the haystack, you better know that it's there to be found. Otherwise, why would you? So the point is that this is a much easier route to identify whether or not you have a hypersurface orthogonal congruence. Okay, other questions? Okay, so that's Frobenius. The last part of that story is to write down Ray-Choudhury's equation. And that will complete the picture, and then we'll have our focusing theorem for null geodesics. Okay, I'm done with that. So that's Ray-Choudhury's equation. The good news here is that we don't have to do any more computation. So all the steps that we carried out when we did it in the timelike case, they just carry over unchanged. So all the steps are exactly the same. And this is a situation where we don't need to worry too much about projection. So from the timelike case, directly importable to the null case, we had this equation for the rate of change of the expansion as we follow the congruence, and we had it in terms of the square of the B tensor minus a term involving the Ricci tensor. So it's exactly the same derivation. The only thing that changes is that instead of having UU here, I have KK because I decided to call UK. But other than that, there are really no other changes. And that's something that follows straight from, just following the steps again from the timelike case. We have to multiply B with itself. But what I really want to come out of this calculation is something involving B tilde. So what we would want to do here is to take this big mess over here and put B on the right-hand side and throw everything else on the left-hand side and then calculate the square of that. So that's a bit of a messy thing. But in fact, it's really not that bad. Because, for example, suppose that I calculate B tilde squared. So let's imagine doing that. So I take B tilde squared, I multiply by B tilde. So B tilde multiplied by B tilde. So let's imagine, squaring that big thing over here. Well, the first thing I would do is to square B. That's what I have over there. The next thing that would happen is that I would multiply B by that. That's 0. Then I multiply B by that, 0. By that, 0. All right, lots of zeros, that's good. Now we multiply this, well, by that, we've done that before, that's 0. Multiply this by that, 0. Multiply this by everything else, 0. So basically, all the other terms are 0. So because B tilde and B differ only by terms involving K, when you square all of this, you find that all the K terms disappear. And the point is that the square of B tilde is actually the square of B itself. So that's a calculation we can do very quickly. We don't even have to write it down. I can claim, and you've agreed with me, that for once, the business of projection is very simple. And now we're really in good shape because squaring this is very easy because, again, we get no interference from the separate parts, right? When we square this, we get h multiplying h, we get our factor of 2, and that kills off this factor of 2. Anyway, so there's factors of 2 in here, so we get something involving theta squared. When we multiply this by that, we get 0 because sigma is by definition trace-free, and multiplying by h means taking the trace. And when we multiply h by omega, we again get 0 because this is symmetric, this is antisymmetric. So we get a term in theta squared, we're going to get a term in sigma squared, we're going to get a term in omega squared. And the same relation that we saw in the timelike case is, is seen again here. So bottom line, the statement of Wright-Choudhury's equation is very similar to what we had before. Instead of a minus 1/3, we get a minus 1/2 theta squared. And then we get sigma squared, we get plus omega squared, and then we get the Ricci term. That's Wright-Choudhury's equation in a null case. Basically, it's identical to what we had before, except that in the timelike case, we would get a 1/3. Again, it has to do with this 1/3 being changed into a 1/2. Is that you raising your hand? No? Okay. Right. Well, that's a very nice equation. And it's nice in this case, and it's even nicer than what we had in the timelike case. Why nicer? In the time-like case, when I wanted to go from this equation to prove a focusing theorem, I had to declare that my congruence had to be hypersurface orthogonal. Well, I still have to do that here. But it turns out to be far less restrictive in the null case than it was in the time-like case. Because often when we want to apply the focusing theorem, and at least that's how we're going to apply it when we talk about black holes, we're going to be given null surfaces. We're going to be given a null surface, and a null surface is always such that you're going to have a network or a congruence of null GDs running across it. So here, the way we approach the situation is that first we're given the congruence, and we ask whether or not there's a bunch of hypersurfaces that are orthogonal to that congruence. And the answer is not always yes. The answer can be no. But if you're given a null surface, like you're given an event horizon, then it's guaranteed that on that null surface, there's going to be a congruence of null GDs running along it. And that congruence, obviously, is going to be hypersurface orthogonal. So for those situations where you're given the null surface, that term automatically goes away. And in those situations which are very relevant, we have a focusing theorem. So focusing theorem. Yeah.
What do you mean exactly by null surface?
It's a surface. Okay. That's a good question. I won't write on this board. So a hypersurface is some restriction on the 4 coordinates of the form a scalar function of all 4 coordinates is constant. The normal to the surface is proportional to the gradient of that scalar function. A null surface is a surface for which the normal is a null vector. Meaning that if I take the normal vector and I calculate its norm, I get 0. That's what I mean by a null surface.
Are there surfaces that the normal switch from timeline to null? Or is that not possible?
Here's a spacetime diagram, Tx. Right? Switches from being space-like to being time-like. And there's going to be a section over here that's null. Or I can draw a null that decides to go time-like, that then decides to go null again, that then decides to go space-like, and so on and so forth. So surfaces can do whatever they want, right? They don't have to be material surfaces. Our word line, if you're a massive observer in space-time and you're moving around in space-time, your word line has to be time-like. It can never turn around like this and decide to be space-like. That just don't happen. So if you're following the motion of a material body, this will never happen. But a surface in space-time is just some mathematical boundary, and it can do whatever it wants, right? So there's really no restriction like that. In that case, only this portion of the surface and this portion of the surface would actually be null. The other portions would be either space-like or time-like. Okay, so back to the focusing theorem. So the first condition is that we have a congruence that's hypersurface orthogonal in this weird sense. At omega 0. And we're going to apply a condition on the Ricci tensor to guarantee that this term is positive or non-negative. And that's called the null energy condition. Now, really, it's only a condition on the, it's really a condition on the Ricci tensor. We may or may not care about the connection between the Ricci tensor and the stress energy tensor. But if we have the field equations, then this guy over here is 8 pi T alpha beta minus half T G alpha beta K alpha K beta. But the second term here doesn't matter because K is a null vector. And down here is really T alpha beta, the components along K. And that has an interpretation as an energy density, at least the limiting case of an energy density as measured by an observer that would move with the speed of light or almost the speed. And then if you say that your spacetime should have only positive energy in it, then you're saying that physically this you would expect to be positive, and therefore you would expect the Ricci tensor to satisfy this criterion as well. So those are the conditions we need to put in to formulate our focusing theorem. And if we have this being positive, the negative sign turns it into a negative number. This would have spoiled the theorem if we had it, but because of the plus, so we remove it. And this is guaranteed to be positive because sigma is a spatial two-dimensional tensor, right? And the square is guaranteed to be positive because it's a spatial tensor. It has no entry along the time direction. A bunch of terms that are negative in here, and that guarantees that, as we had in the timelike case, the rate of change of the expansion has to be negative, or at least non-positive. You had a question?
Should that T alpha beta minus half T not be half R? Because it's the Einstein equation, so it should be R, not T. That T alpha beta minus half capital R.
I'm sorry, I'm not getting that.
You have minus half T G alpha beta there.
Yeah.
Should that not be an R for the Ricci scalar?
You can reverse the Einstein equation.
So the Einstein field equations are G equals T, or those are two ways to write down the field equations. And you can check that just taking the trace, so the trace of the Einstein tensor G is minus the trace of the Ricci scalar, which is 8 pi times the trace of the integer momentum tensor. So when you put it all there, you can go from here to there. Right, so that's the statement of the focusing theorem. And again, it means the same thing it meant last week. So if you have a congruence that's initially diverging, it will diverge less rapidly in the future. If you have a congruence that's initially converging, it's going to converge more rapidly into the future. And if it's converging and it continues to converge more rapidly, it's going to converge catastrophically at some point, and you're going to get caustics forming. You're going to have crossings of geodesics. So theta initially negative leads to crossings, which is the same thing as saying caustic formation. That turns out to play a very important role in the context of black holes, because again, in the case of black holes, we are given the event horizon, which it's a boundary between the inside and the outside. It's a causal boundary in your space-time. If you don't want to lose the black hole, if you don't want the black hole to stop being a black hole, or said better, if you want a black hole, that boundary has to exist forever, right? You can never leak out of the black hole so that event horizon cannot have any holes in it. So it has to exist in the future. The congruence that's everywhere tangent to the event horizon cannot have crossing points. because if it had a crossing point, you could not guarantee that after crossing that the geodesics be on the surface. If you have caustics forming in a congruence, even if it's hypersurface orthogonal, after crossings, all hell breaks loose and you can leak out of the surface. So black hole event horizons cannot have caustics like this. You cannot have a place on the event horizon where the expansion starts out negative.
Are you going to say more about that in another lecture?
Oh, of course. You know, when we talk about black holes, I'll give you the full story, a lot more about this. This is just a little bit of a preview. But the point is that if you have an event horizon and you want to keep it, you cannot have caustics. If you don't want caustics, you cannot have anywhere on the horizon that has a negative expansion. That is, you cannot have converging geodesics. The null geodesics cannot be converging. If they are converging, they will keep on converging faster, and that's how you're going to get acoustics. Therefore, your event horizon has to be such that the geodesics are either expanding or remaining stationary. That's the area theorem.
What was wrong with caustics? You said it leaks out of the surface. I didn't
Right.
get that point.
No, it's not obvious. It's not meant to be obvious. The point is that, so if you have a nice null hypersurface, if it's to be a smooth hypersurface, if it's to be a hypersurface defined over, a big range of times, it has to be true that the congruence that runs on it is also smooth. And it cannot have singularities in it, and it cannot have caustics in it. If you had a situation where you had a hypersurface for a while and you had caustic formation, you cannot guarantee that there will be a hypersurface on future of caustics. That's what I meant by leaking out of the surface. So if you have a singularity in the congruence, you cannot guarantee that the surface will keep on existing as a smooth surface. And the way I like to think about this is just that, well, picture you have the surface, when you have the surface, you have crossings of geodesics. Well, after crossing, you've created a singularity in the flow of your null geodesics. The future behavior beyond that singularity is not predictable. And therefore, you cannot guarantee that the geodesics will stay on the surface as opposed to, crossing out or in. That's what I meant.
But maybe my point is, we know that singularities exist in nature.
Yep.
So why, to avoid singularities of this kind, say that they shouldn't exist or?
Okay, they do exist. They certainly do exist inside black holes. But if we are going to talk about black holes, we have to talk about event horizons that persist. And if you don't have an event horizon that persists, you don't have a causal boundary in your space-time between the exterior of the black hole and the interior of the black hole. So if we're going to talk about black holes at all, we have to talk about a smooth event horizon that extends forward in time forever. And if we want that, we have to have a congruence that doesn't converge. And if the congruence is not converging, it's either expanding or keeping still. But if it's not converging, that means that the area of the event horizon cannot be decreasing. That's the area theorem. So we'll come back to that, and I'm just throwing that at you because it's all, coming out of the consequence of the focusing theorem, which is itself, a consequence of Ray-Choudhury's equation. But that's just to tell you that there's a lot of power here that will tap, when it's time to talk about black holes. There's a lot of very good stuff here. One final remark, and then I'll quit. We've talked about things not being unique because of this non-uniqueness of the vector n. It would be disturbing if this beautiful theorem, for example, would only be valid for one choice of n and may not be true for other choices of n. So the way it goes is this. Theta is unique, independent of n. sigma and omega are not. So you change your n, you'll change your sigma, you'll change your omega. However, sigma square and omega square are unique. Which means that each term in this equation is independent of n. So Ricciardui's equation is independent of n. And the statement of the focusing theorem is independent of n. This being unique and sigma being a spatial tensor means that if, for example, you find that sigma is 0 for one choice of n, it's got to be 0 for all choices. Because if it's 0 for one choice of n, that's the only way that sigma squared can be 0. And if sigma squared is 0 and it's unique, then it's got to be, so sigma squared being 0 means that sigma itself has to be 0. And if this is unique, then the sigma that we get out of it has to be unique as well. And that's the same for omega. Omega squared is unique. Omega squared can only be 0 if omega itself is 0. And that statement is also independent of n. So the statement of hypersurface orthogonality is independent of n. So if you do a calculation where I'm giving you, a tangent vector field k, and then you go and pick your favorite n, and you do the calculation of omega to decide whether or not it's hypersurface orthogonal, if you find that for your n, omega is 0, then you can be sure that it's going to be 0 for any choice of n. And that therefore the conclusion that it's hypersurface orthogonal is not, subjected to. So it's good, because otherwise it would, nothing would make sense if that were true, right? If that was not true, we would be in trouble, and these calculations would be very meaningless. That's not obvious. You have to do a bit of work to prove these statements, and in the next homework assignment, I'll ask you to go through that. It takes some work, but it's doable, and you can work out basically the transformation properties of each of those quantities under a change in n. So if you pick a different n, you can figure out how these things will change given the change. Okay, so that wraps up chapter 2. So next week we're going to be launching into chapter 3, which is all about hypersurfaces. So some of what we've talked about will come back, but now we'll do it more systematically. And again, we're going to go from time-like and space-like, which are easy, to null, which is, again, subtle and subject to all sorts of little puzzles. So we're going to have fun with that for a while. Any questions about any of this? No? Okay, so I'll